I wanted to talk about section 2.3, so I kind of thought maybe I would get a running start and do a couple of examples from 2.2. With this picture, the limit as x approaches 1 from below of this function h of x is what single value is the function getting close to, or the y value is getting close to, if x is close to 1 but a little bit smaller than 1. I hope you can see that it seems to be getting really close to, it actually doesn't hit, there's a circle here, but it seems to be getting really, really close to 1. On the other hand, the limit as x approaches 1 from above of h of x is, if the input value x is close to 1 but a little bit bigger, then the function's going to be way up here. This is obviously a piecewise defined function. This is up here, this is 4. And as it turns out, h of 1 is about 2.5, which is not the same as either of these. Sorry. The point is that the limit doesn't care what happens when x is equal to 1. The limit only cares about what happens when x is near 1. Since we have this here, alternate universe number 39, if we looked for the limit as x approaches 0 from below of this function, or the limit as x approaches 0 from above, or for that matter, the plain vanilla limit, when this function gets close to 0, the output value is close to 0 from the left or the right or from both sides. And as it happens, the function value happens to be the same as what the limit is. That's a cool, handy property that we'll study later. But for right now, the limit doesn't care. This is just a lucky accident. You know what? I kind of wish this one had also included a part C. The limit as x approaches 1 of h of x is, the limit as x approaches 1 doesn't exist because the left limit and the right limit, the limit from below and the limit from above, aren't the same thing. If the left limit and the right limit aren't the same thing, that's enough to say that the overall limit doesn't exist. Let's do another one. For 45, the book only has part A and part B, but I hope when you think about part A and part B, you think about part C as well. Which of these three is going to be easiest? Which is going to be hardest? To my eye, I would say the easiest one is probably B. If x is close to 0, if x is close to 0, if the input value is close to 0 but a little bit bigger than 0, then the output value is going to be really, really close to 0. If x is close to 0 but a little bit smaller than 0, this funny notation means that the function is bouncing back and forth, up and down, infinitely many times. The graph of sine of 1 over x or cosine of 1 over x has that kind of behavior. This does not exist. This limit didn't exist because the left limit and the right limit were different. That's sometimes called a jump discontinuity. This limit fails to exist because the function values are just bouncing all the heck all over the place. There's not a single value that they're getting close to. You can kind of see, I hope this picture indicates that the function values are going all the way up to 1 and all the way down to -1 and all the way back up to 1 and all the way down to -1 again and again and again on any little interval. The fact that the left limit and the right limit don't agree, in fact one of them doesn't exist, is enough to say that this doesn't exist. I can't tell for sure from this picture if h of 0 is actually 0, is what it kind of looks like, or maybe h of 0 is undefined, or maybe h of 0 is something else. But the point is that the limit doesn't care. The idea of the limit is the value that a function is getting close to without caring about what happens at the actual target value, just about what happens near the target input value. All right. Most of you are okay with that. I just kind of wanted to walk through a couple at the beginning because the definition is fiddly. The definition is awkward. I'm going to jump ahead. I don't hate these examples, but several of them have numbers that are so simple that you're kind of missing what's going on. So I just made up my own. Prove that the limit as x approaches 7 of the quantity 3x plus 5 is equal to. If I ask you to find that limit, I hope everyone can see if x is close to 7, then 3 times that's going to be pretty close to 3 times 7, that's 21. And 5 more than that is going to be pretty close to 5 more than 21, that's just 26. Finding the limit is using the idea of the limit, and that behaves the way it's supposed to. Proving that this is true, it's not enough to just plug in 7, because remember, the limit doesn't care about what happens when x equals 7. To prove this, that means walking through that epsilon delta definition. This word means I may need more paper. That epsilon delta definition says the limit as x approaches a of f of x is equal to L means that for any epsilon greater than 0, there is some delta greater than 0, so that means so that x being this close to its target guarantees or implies there are good homework exercises. This is a hard thing to ask online, so the homework exercises are a bit more like these specific example values. for a particular epsilon equals 1/10, find a delta that would satisfy this, and sometimes find the best delta that would satisfy this for a particular choice of epsilon. But the actual definition says no matter what epsilon you pick, somehow show that there is a delta, so that if this happens, then this happens. I really do want bigger paper, so let me... Maybe I'll keep that handy so I can see that definition, and we'll work it. If I want to prove this, the way you prove it is you start with any epsilon greater than 0. And then somehow I have to prescribe a choice for delta something, so that once I've picked this delta, if x is delta close to a, except possibly at a, then the function value is going to be epsilon close to L. What should this be? I don't know until I figure it out. And figuring it out usually means working backwards. I'd like to be able to end with saying that the absolute value of the function, the absolute value of the difference between the function value and its target is less than epsilon. In our case, the absolute value of 3x plus 5 subtract 26 is less than epsilon. That means 3x plus 5 minus 26, that's 3x minus 21, is less than epsilon. And this is 3 times the quantity, x minus 7, that's less than epsilon. Properties of absolute values tell me that the absolute value of 3 times this is the absolute value of 3, which is just 3 times the absolute value of x minus 7. And now I can see that if I divide each side by 3, this is the delta I need to use. Actually, any delta smaller than that is still going to do the job, but this is sort of right at the edge. Now set delta to be epsilon over 3. Epsilon could be a tenth, epsilon could be a hundredth, epsilon could be a millionth. No matter what the epsilon value is, no matter how tiny the epsilon value is, I can cook up a delta value. I'm just going to take epsilon over 3. Then whenever zero is less than absolute value of x minus 7 is less than delta, because delta was epsilon over 3, And if this is true, I can multiply each side of this inequality by 3. Remember, if I multiply each side of an inequality by a negative, I have to switch the direction. But 3 is positive, so and 3 times this absolute value is going to be the same as absolute value of 3 times this quantity. This is 3x minus 21. And 3x minus 21 is 3x plus 5 minus 26 inside that absolute value as required. This was the punchline. I mean, literally, this is the punchline, and this is the joke to get to that punchline. And honestly, this works for actual jokes. Sometimes you have a punchline, and you have to determine the setup that's going to lead to that. That's how we prove that a limit is a particular value. There are some variations if we're looking at limits at infinity or other things, but this is the most basic form. There's a left-sided version and a right-sided version. All of those are slight variations. There are more complicated examples. I said that I didn't hate them, I just didn't love them. The examples here where they asked us to prove things. In part because some of these are kind of so easy that you could stumble over it without really knowing what you're doing. The linear functions are reasonably straightforward. Quadratics and cubics and other things get complicated quickly. This epsilon delta definition is important and useful and worthwhile, and it turns into a monumental pain in the rear if you try to do it in any depth. If you find this interesting or challenging in a good way, I would suggest that you consider taking a class called mathematical analysis or real analysis in your future. Real analysis is essentially calculus done carefully. Every time we sort of look at something and don't nail down all of the details or say we'll save them for later, that's the time when those get nailed down and verified. That's a worthwhile class, but that's not this class. This is just an introduction to calculus, a first semester Calculus 1 class. Let's maybe look at one of these with an infinite limit. And 50 looks cute. Let me see if I can shrink this down. Give the formal definition of the limit claim, then use the definition to prove the claim. That could be a little bit bigger. Yeah, that's better. Oops, sorry. I hope everyone can see this. I hope everyone can believe that if x gets big enough, 1 plus 3x cubed, if I divide that by x cubed, 1 divided by x cubed is going to be negligible, and 3x cubed divided by x cubed is just going to be 3. So this whole thing is going to get really, really close to 3. I hope that's believable and comfortable. Proving that is a little more work. So let's write out the statement. The limit as x gets large of a function equals some target value means that for any epsilon greater than 0, there is some not delta n, so that in the normal limit definition statement, this is epsilon and delta. If you look this up online, you sometimes see funny symbols. So for any epsilon greater than 0, there's an upside down A that means for any epsilon greater than 0. And there exists some delta. You'll sometimes see a backwards E, delta greater than 0. For any small enough value, however small you want value of epsilon, there exists some small value of delta so that this happens. I'm in a slightly different situation, so no matter what tiny epsilon you might pick, there's a far enough out, there's a big enough n value so that x being bigger than n guarantees that the function value is within epsilon of its target. The difference between the function value and this target value is less than epsilon. Recognize that that says what it ought to say. Let's look at it in the context of this one. Limit x gets large of 1 plus thrice x cubed, divide that by x cubed, equals 3, means that no matter what epsilon you pick, positive, so the book saying write out the definition statement and use it to prove this. Proving this means you'd start with an arbitrary epsilon. Then describe some value of n. And I don't know what that choice is until I figure out what I want to happen. What I want to happen is this. And this is really starting at the punchline and working backwards. This is 1 plus 3x cubed over x cubed. If I want to combine fractions, I need common denominators. This is 1 plus 3x cubed minus 3x cubed. This is just 1 over x cubed. That's less than epsilon. And the absolute value of 1 over x cubed is 1 over the absolute value of x cubed. And if x is positive, then this would mean that absolute value of x cubed is greater than 1 over epsilon. I could take the reciprocal of each side. And absolute value of x is greater than, I could take the cube root of each side. This is the n that I need. I need to make sure that n is positive and it's bigger than this. So let's set n to be the maximum of, you know what? If epsilon is greater than 0, then 1 over epsilon is going to be greater than 0. And the cube root of 1 over epsilon is going to be greater than 0. So n is guaranteed to be greater than 0. Okay, that's not really a problem. Let's set n equal to the cube root of the reciprocal of epsilon. Excuse me. N is positive, so x is bigger. Means it's also positive. These are both positive. That means that x cubed is bigger than 1 over epsilon. And that means that 1 over x cubed is less than epsilon. And 1 over x cubed is this expression is this expression. And this expression is positive, so the absolute value of this expression is the same thing as itself. This is equal to this, and we know that this is positive, so it's its own absolute value. And that's what I was trying to show. I was trying to show that there's an n value so that anytime x is bigger than that, I'm guaranteed that the function value is within epsilon of 3. In this case, we knew that it was always below that. Sometimes it might be above or below, and that's okay. In different settings, we sometimes have to pay a little more attention. But ultimately, we're walking through a very similar argument to what we did with this epsilon delta argument. This is a pain in the rear. This is important and worthwhile, but it's fiddly and tedious. I don't want to be doing this all the time. I do think it's worthwhile to do this a few times, which is why we have section 2.3. But I don't want to have to be doing this all the time, which is why there's section 2.4. Section 2.4 says, you know what, now that we've walked through the definition, sweet heaven, let us do it an easier way. There are easier ways, there are limit laws, there are properties we can take advantage of so that we don't have to always use the definition every time. But that only is meaningful, that's only worthwhile if you've actually used the definition. So you really have to, get through the 2.3 stuff. 2.4 says the limit of a sum is the same as the sum of the individual limits, if they both exist. The limit of a difference is the same as the difference of the individual limits, if they both exist. The limit of a constant multiple of a function is that constant multiple of the limit of that function. These all work exactly the way you expect them to. Be careful this denominator isn't 0. And the proof of these, there's the proof of the sum law here, and the others are in the appendix. They all walk through using the definition of the limit. So you really have to read and familiarize yourself with that epsilon delta definition to see why these work. They're legitimate. Don't believe it just because Holly Buchanan says so. Don't believe it because Paul Sisson says so. Don't believe it because it's printed in your book. Believe it because it's legitimate. I mean, no matter what function you have and what other function you have, if this limit exists and this limit exists, then we can prove that the limit of the sum of those two functions is the sum of the limits using an epsilon delta definition. And the idea is whatever epsilon you pick, take half of that and find a delta value for the first function for half epsilon, and find a delta value for the second function using half epsilon, and then using those two different delta values, take the smaller of those. I would write let delta be the minimum of delta 1 and delta 2. And since it's smaller than each of them, this is going to be satisfied, and this is less than epsilon over 2. And this is less than epsilon over 2. So their sum is less than epsilon. That's cool and important and worthwhile. But it uses that epsilon delta definition. And these 5 basic limit laws are exactly the same limit laws if you have limit as x approaches c from below, c from below, c from below, or limit as x approaches c from above, c from above, c from above, or limits at infinity, limit as x approaches infinity of k times f of x is equal to k times the limit as x approaches infinity of f of x. All of those different variants are going to have exactly these same limit laws. And the limit laws mean that we don't have to walk through the definition every bloody time. thank heaven, the limit of this product, if I can see what the limit is when x approaches 2 of f of x, and the limit as x approaches 2 of g of x, then the limit of this product is just going to be the product of those two limits. When x approaches 2, let's see, the f function is the blue function. Looks like the function value is getting close to 7. The g function's getting close to 3. The g function at 2 is down here at 2, but I don't care. Limits don't care about what happens at a target input value. They only care about what happens nearby. And for x values close to 2 but not equal to 2, the function value is nearly 3. So the limit of this product is just going to be the product of those two limits. 7 times 3, that's 21. That's pretty slick and sweet and handy, and I love it. I appreciate it. I'm glad of that. I'm glad I don't have to walk through the definition every single time. There are more examples. If you repeat the product rule, you get the positive integer power law. You could imagine multiplying a function by itself, or multiplying it by itself, or multiplying itself by itself, by itself, by itself. Whatever exponent, whatever positive integer power you might want to raise this to, you could imagine splitting that up into separate product rules. And if this limit exists, then I'm just going to get that limit raised to this power. And in particular, if it's just plain x, then I'm going to get exactly the same as what the polynomial spits out. These don't mean the same thing. This means the function value if you plug c into the polynomial. This means the limit as x approaches c of this polynomial function when x is close to c. But it happens to be the case that, I mean, it's not an accident. It's a lucky, it's a handy, it's an important, useful, and worthwhile property that for polynomial functions, the limit doesn't care about what happens if you just plug in that value, but as it turns out, the limit is exactly the same as what the value is if you just plug in that value. That's pretty cool. And the same statement for rational functions, for polynomials divided by polynomials. As long as the denominator isn't 0, the limit of a rational function, and that's really just a repeated application of the sum and difference and constant multiple and that power rule that we just saw. Here are some examples. As always, if anything's unclear, let me know and we can come back to it. I kind of want to wrap this up. If we look at rational roots, then we have the same statement that we had for rational power, for integer powers. The proof of this actually takes something that we're not going to get to until later, but it's handy to have it. So we're going to go ahead and introduce it slightly out of order so that we've got this rational power law. That's handy. That's cool. That's good. That means that the limits are what you would hope that they would be. Again, the limit doesn't mean the value when you plug in this input. It's just that in the case of rational functions, functions raised to a rational power, this is a rational function, and this is a rational exponent. This is a polynomial divided by a polynomial, so the limit when x approaches 1 of this is going to be the same as what you get if you plug in that value. The limit means something different, but the value ends up being just the same number as what you get if you plug in that value. And then raising that to the 7/3 power gives me this. functions that have this really cool property, the direct substitution property, are called continuous, and we're going to study continuous functions in some detail later. It's worth noting that sometimes you don't get off easy. The limit as x approaches -3 of this expression, I can't just plug in -3 because the denominator would be 0. However, the limit doesn't care about what happens when x equals -3. This rational expression is undefined when x equals -3, but a little bit of algebraic simplification would let me say, as long as x isn't -3, this expression is equivalent to this expression. And this expression I can evaluate when x equals -3. That's cool and handy and worthwhile. These are not exactly the same picture. These are the same picture, except this one has a hole. This one is undefined when x is equal to -3. This one is defined when x equals -3. And these have exactly the same limit. Remember, the limit doesn't care about what happens at a target input value. It only cares about what happens near a target input value. And except for that one missing point, this function and this function are identical. So the limit for this one, which is awkward, is going to be exactly the same as the limit for this one, which is drop dead easy. There's another cool theorem about limits. If I've got one function stuck between two other functions, if I've got a big function and a little function, and the one I'm interested in is between the big function and the little function, for all input values, actually for all input values on some open interval around my target input point, if the big function and the little function have the same limit at this target point, then the one stuck between has the same limit at that target input point. Here's a good example. X times sine of 1 over x when x approaches 0. Sine of 1 over x when x approaches 0, remember that's the thing that bounces up and down. But this is smaller because the sine function is always between 1 and -1. This is stuck between absolute value of x and opposite of absolute value of x. And each one of those, when x gets close to 0, gets close to 0. So this bad boy's bouncing up and down all the time, but it still bounces up and down sandwiched between these. The squeeze theorem tells us that the limit of this weird function is the same as the limit, because the limit of the bigger function and the limit of the smaller function, this one is too big and this one is too small. They're both 0, so the one stuck between is also 0. One last theorem in this section. If one function is smaller than another function, except possibly at the target point, and the limits both exist, then the smaller function has a smaller limit. That shouldn't be surprising. Actually, proving that is a bit of work, and we're not going to fool with it. You're not responsible for proving all of those things. We are responsible for understanding and using all of those things. Do finish the 2-3 stuff first. I mean, if you skip the 2-3 stuff, you're still allowed to do later homework, but it's going to make sense, and I promise you it's going to show up on the exams. After you've done the 2-3 stuff, please read section 2.4, which is properties of limits, limit laws. And do the certification and then paper homework, pages 156 and 157, every other odd, and through 53, and odds 55 to 63. I recommend doing paper homework because not everything in the world looks like online exercises. When we get to midterm time and final exam time, I am not an online software platform. I am not going to ask you the kind of questions that online software platforms ask. I'm not trying to be mean to anyone. I'm not trying to throw you curveballs. I'm trying desperately to let you know ahead of time what to expect, and doing paperwork is closer to what the midterm and final exam will be than the online exercises. I like the online exercises. I like the online platform. I like Hawks. I like the nearly instantaneous feedback. I, as a human, am a slow grader. I like the fact that you can get instant feedback from Hawks. But I also recognize that there are some types of questions that are just awkward online and much more manageable on paper. Okay, as always, if you have any questions or problems, let me know and I'll be glad to help anyone with anything.